Hello, good afternoon, everyone. Has anyone in the audience ever come across an error page like this before, where it says, hang on a sec, our site's experiencing more traffic than usual, but you should be able to get back to shopping shortly? Raise your hands if you have. Right, so there's actually quite a few of you in the audience, and I did some research about this, and it turns out it's pretty common. Even the most reputable sites displayed this type of error message about not being able to handle the level of traffic that's hitting their application. And as a result, users are not able to access the site. Even Amazon. On Amazon Prime Day, as I'm sure you can all imagine, there was a huge spike in traffic on their site. And as a result, users were experiencing a similar error page. They couldn't access the site and make the purchases they wanted to make. But going back to the jQuery experience, I have to be honest about it. I was slightly embarrassed, if not disappointed. When I visited this site, I was thinking of my user experience as the customer, not being able to make the purchase I wanted to make. But I never thought about it from the other perspective. I build websites just like the ones above. And never once did I think, could my users be having a similar experience? Hi, my name is Katie Koschland, and I'm an engineer. I work at the Financial Times, and today I'm going to talk about my load testing journey. And I will aim to cover the core concepts behind load testing. I'll start with the challenge, and this is how I came across the topic of load testing. I'll then go on to explain what it means to load test your application and how you can get started with writing your own scripts. I'll then go on to explain how you can use the metrics to help identify a performance issue within your application and discuss the tools and techniques we use at the FT to help troubleshoot and improve such performance issues. And finally, I'll conclude with some outcomes. The challenge. I recently finished a 3-month secondment in the Operations and Reliability Engineering team, where they were developing the BizOps API. The purpose of the BizOps API was to provide a central store for all business information at the FT. Above illustrates the model, and you can see the type of information that would be retrieved from the BizOps API. It provides information about our systems, how our systems relate to each other, and how those go on to relate to groups and teams and people who are working at the FT. So it was really important for us to be able to understand the technical limits of our application, as it was going to be used frequently across the FT. So that was my challenge, testing the technical limits of our Node application. But more specifically than that, could I answer the following 3 questions? Will our application crash? If so, can our application recover? And what exactly happens to the user experience? Once we have found the application's limit and we've pushed past it, does the user experience degrade gracefully, or does it actually just cause absolute meltdown? And I was told that the answers could be found by load testing our application. So what exactly is load testing? A colleague of mine recommended an excellent talk by Jad Mauchi, where he describes load testing in simple terms. It's about simulating ordinary user activity and then applying stress until it reaches failure. I really like this explanation, but it kind of led me to my next question, which is, how can I apply this so-called stress to my application? First, you need to decide on a testing framework. There are many frameworks out there, including popular ones like Apache Bench, Locust, Artillery, Work, Gatling. But I decided to go with Artillery. and it was for the following 5 reasons. First, it could be installed using npm, which was really a no-brainer if I wanted to get started quickly. And next, it allows you to customize JavaScript code within your own scripts. And this was particularly helpful for a situation where we wanted to generate random write queries. It meant I could write it as a separate function and then call it in my test script for each virtual user request. It was also helpful if you wanted to write a separate function that sets the headers or cookies. Above is an example of my JavaScript function that sets the headers for each request. So all I have to do in my script is call this function each time a virtual user made a request. Another advantage was that scripts could be configured using YAML. Above is a snapshot of one of the scripts I had written, and you can see by writing it in YAML, it makes the test scripts very easy to read and maintain. You can also see here that I'm calling the setHeaders function that I showed you previously. And it's also targeted towards continuous integration. Unfortunately, I didn't have a chance to implement this, but this is something that's particularly interesting and I'd like to implement in the future. If performance is a high priority within your application, what you can do is you can configure your continuous integration, let's say Circle CI, and it can run your script each time you trigger a build. This way, you're able to detect at each point of your development process how a feature directly impacts the performance of your application. It also allows you to detect any regressions in your application. And finally, it provides detailed metrics, which I'll go on to explain shortly. So once you've decided the testing framework that's suitable for your application, then you need to think about what type of requests that could be hitting your application. Your test scripts need to be able to represent ordinary user activity. Think about the common user journeys on your site and try to capture those type of requests that the user's making. This way, you can replicate the exact behavior in your script so your virtual users are making the same requests as your real-life users. Next, you need to decide on the shape of load that will be hitting the application. You're probably thinking, what do I mean by the shape of load? Take this graph above as an example. It illustrates the shape of load that was hitting ft.com homepage during the 2017 election results. You have time across the x-axis and then the number of user requests on the y-axis. So you can see how the shape of load changes over time quite drastically. There are peaks where the number of concurrent requests per minute are very high, causing a huge spike in traffic. But then there are also troughs where there are significantly lower level of concurrent requests per minute. So you want your scripts to test the different shapes of load that could potentially be hitting the application over a period of time. And this can be challenging. Before production, it's difficult to predict the number of concurrent requests or how they would ramp in over time to the application. However, this was really crucial if you want your tests to be as robust as possible. So if your application's already in production, you might already know the shape of load that you want to test. But it's also okay if you don't know about the shape of load for your application. As the BizOps API was still in the development stage, it was difficult to predict the number of concurrent requests and how they'd ramp in over time. However, this was really crucial if I wanted my script to be as robust as possible. If this is the case, you might want to consider splitting your script into 4 phases. This way, your script is capturing the different shapes of traffic that could be hitting your application over the production cycle. Depending on the size of your application, can depend on how you define these separate phases to determine the correct number of virtual requests per second. But I'll show you what I decided that I thought was appropriate for the scale of our application. First, I defined a warm-up phase, and this was the arrival rate of 10 virtual users per second that lasted for 60 seconds. Next, it was a ramp-up phase. This was the arrival rate from 10 to 25 new virtual users per second for 120 seconds. Next, I defined a cruise phase. That was the arrival rate of 25 virtual users per second for 1,200 seconds. And finally, I defined a crash phase. This is the concept of finding the limit and pushing past it. It was the arrival rate of 100 virtual users per second for the short burst of 30 seconds. But it's really important to note that there's no point hitting your application with a load that you know it can handle. The purpose of this phase is to make the application crash. You want to be able to understand the exact behavior of your application once you've pushed past its limit. Once it's crashed, will it be able to recover on its own? If so, how long will it take for it to recover? Or will it require an engineer to come in late at night to fix the issue? These are the types of questions you want to be able to answer from the crash phase. To visualize this, I've identified these 4 phases in a production cycle. Again, it's a graph showing the number of requests per second hitting the ft.com homepage over a 24-hour period. From 12 a.m. to 6 a.m., there's a low level of requests per second of 5. And this is what I defined earlier as the warm-up phase. From 6 a.m. to 9 a.m., there's this gradual increase in the number of requests per second from 5 to 11. Clearly, this is during our users' daily commute. And then from 9 a.m. to midday, there's a constant rate of about 11 requests per second, which is what I define as the cruise phase. And then what I've done is I've extrapolated the graph to demonstrate what I think the crash phase would be for the size of this application. And this was about 40 requests per second. So you've made decisions on the testing framework, the type of request, and the shape of load. You're ready to write your script. So we need to discuss getting started. What should your first script look like? The script should be split into 2 sections. First, the config section. You start by choosing the target of your load test, so the address of the API server under test. In our case, it was the BizOps API staging endpoint. Our staging environment was an exact replication of a production environment, so we were able to test staging as it was an accurate representation of production. Then, you can specify any plugins you'd like to use. We used a plugin that allowed us to send the output of our loads tests to Graphite and Grafana. Graphite is our metrics data store, and Grafana is the presentation and data visualization layer. This helped us monitor the metrics over time and created graphs that later on helped with troubleshooting. Then you define the load phases. This is what we discussed previously about the number of concurrent virtual users and the method of how they ramp in. And then the processor. This is where you import any JavaScript files that contain functions you want to use in your script. So above is a snapshot of essentially what your config section should contain. Next, you have the scenarios section. This is where you identify what the virtual user's behavior is going to be during the test. So you define the type of request that the user is going to make. You start with naming the virtual user request. In this case, the user request was going to retrieve a list of all the systems at the FT and their corresponding properties. Then you define the flow. This is an array of operations that a virtual user will perform. In the above example, they're making a post request with a JSON body that contains a GraphQL query. You can see here that I'm also calling my setHeaders function before the request. And above is a snapshot. You can add as many operations as you'd like. In my script, I had about 5 different read queries that were going to be made by a virtual user. It's also important to note that if you wanted to, you could also assign weights to the queries. A weight allows for the probability of a scenario being picked by a new virtual user to be weighed relative to other scenarios. We didn't do this, but above I've showed an example of how you would assign a weight to your script. Let's say I make an assumption that users are twice more likely to make a request to retrieve systems than query health checks that are live. I could assign a weight of 2 to the first query and then assign a weight of 1 to the second query, and it's as simple as that. Once you're happy with a script and you've put both the config and scenario section together, you're then ready to go. And you can run the load test using the following command: artillery, run, file path, and the name of your script. Okay, so what happens after you run the script? So artillery will provide you with a summary report that contains detailed metrics, and this will help analyze the behavior of your application when it's under load. So you have scenarios launched. That's the number of virtual users that have launched a scenario throughout the test. You have scenarios completed. This is the number of virtual users that have completed a scenario throughout the test. And you've got requests completed. This is the total number of HTTP requests and responses sent. And you've got RPS, the average number of requests per second completed throughout the test. And status codes, the HTTP status code responses from each request that's been completed. And finally, you have the request latency. This is how long it takes the server to receive and process a request, and it's measured in milliseconds. So we understand what the metrics mean, but how can we actually use the metrics to identify a performance issue? Above is an example of one of the summary reports from our script. You can see we noticed that the request latency had started to grade rapidly during our load test. It began with 67.6 milliseconds and then suddenly ramped up to reaching a median request latency that exceeded 30,000 milliseconds. This was really concerning, as we were only on average sending 20 requests per second, and we were expecting our application to be able to handle a much higher number of concurrent requests. Also, out of the 6,000 scenarios launched and completed, more than 90% of requests received an HTTP status code 500, indicating the server was aware of an error or simply incapable of performing the request. And there were also 503s, indicating it couldn't hit the server at all. So the metrics about the response times, the throughput rates, and status codes helped identify a serious performance issue early on in the development process that would essentially stop our application from running. Right, so now we've got this performance issue. How do we find the culprit? We ran several tests singling out each query and sending the metrics to Graphite and Grafana. After a couple of attempts, we found the culprit. It was this GraphQL query which was trying to retrieve the first 600 systems that had a bronze service tier. In fact, we were reaching 100% CPU when running this query, and it was at a very low rate of 10 requests per second. CPU is the central processing unit in the computer that does all the computational work. So the fact that we were reaching 100% CPU utilization with this very low level of requests per second led us to believe it was perhaps an application issue. So we wanted to determine whether there was something in our code base that was causing the CPU to reach 100% utilization. A good starting point was to generate a flame graph in order to profile the CPU usage. We used the plugin 0x. Again, it could be installed using npm, and with the second command, it would generate the flame graph for you and open it in a separate browser. So it was very quick and friendly to use. Above is the flame graph we generated. With a flame graph, all the data is on the screen at the same time, and the hottest code paths are immediately obvious as the widest functions. Annoyingly, though, there was nothing unusual being displayed. There was no single line of code using up the whole CPU usage that we could try to fix. So we needed to think about what else could be causing the performance issue. Our database is a Neo4j instance run by GrapheneDB. So when a user makes a read query using GraphQL, it hits an execution layer. In our case, it was an npm module called Neo4j GraphQL.js. And that will translate the GraphQL query into a Cypher query. So if you take the query that was causing the performance issue, it would get translated into this Cypher query. And then this would then be sent directly as a request to our Neo4j instance. So we decided to look into configuration of this NPM module and see whether we could identify a performance issue there. We noticed that the driver had a maximum pool size of 100 connections, and this meant that if a session tried to acquire a connection, but the pool size was at capacity, it would have to wait until a free connection was available, or the request would time out, causing an HTTP status code 503. This seemed to suggest we could face a performance issue if the number of connections were exceeding the limit when running our test. So we increased the pool size to 300 and decreased the retry timeout to 10 seconds to see if this would resolve the problem. But we weren't hitting the capacity of 100 connections, so increasing the pool size had no impact on the overall performance. So we looked at Cypher tuning. Thankfully, with Neo4j, you're able to see how a particular query performs by prefixing it with profile. This isn't specific to Neo4j and can also be done with other databases such as SQL. So we ran profile on that particular query that was causing the problem, and this was the output. What we're interested to see here is the total number of database hits from the query, which was 14,213. The objective of query profiling is to find a way in which you can reduce the number of database hits required to perform the task whilst keeping the output level constant. So, one way you can reduce the number of database hits is to create an index on the starting point of your query. We created an index on service tier attribute in the hope that this would help improve the performance of the query. And we ran profile again. The number of database hits did reduce by 2,148. However, it didn't resolve the performance issue or even have much of an impact at all. So we then looked at the configuration of our Neo4j instance. What was the size of the instance? Do we have the correct RAM size? And what are the number of cores on our server? We started by running system info in the Neo4j browser, which provide us information about the size of our database. For example, information about the number of nodes, the number of relationships in our Neo4j instance. For this, we could use the Neo4j hardware sizing calculator, and it recommended to increase the size of total RAM and also the number of cores we had on our server. This could explain why the CPU was maxing out. And we discovered that our current plan was also on a shared resource. So we upgraded the plan to Performance 1, which had 8 gigabytes of RAM and 2 cores on the server. However, confusingly, when we ran the script again, even with a dedicated resource, the overall performance had actually got worse. So this led us to believe that it could be a network I/O bound issue. So you're probably thinking, I've done all these troubleshooting techniques, but come on already, like what was the fix? Unfortunately, from one day to the next, the performance issue just disappeared. We were all of a sudden able to make 25 requests per second without our application crashing. So for this particular example, we were unable to find the solution to the problem. So why have I shared this example with you and not one where I actually managed to fix the performance? Because what I learned from this is invaluable, and I want to be able to share this with you. I've been able to build a personal toolbox with tools and techniques that will help me identify and eradicate future culprits. But also, there were practical outcomes. First, we were able to measure, assess, and improve the overall performance of our application. By load testing, we were able to detect a performance issue early on, and as a result, dedicate time to help improve the overall performance of our application before it went into production. We were also able to assess the reliability of our application. By load testing, we had increased our confidence that our application could stay online given a certain level of traffic, and understood exactly at what point we would need to consider scaling our application in order for it to carry on staying online. So, to conclude, if you want to fully understand the performance and reliability of what you're building, you should all consider load testing your application. Thank you for listening. and we're also hiring, so visit the site or come chat to me.